All right, so we are already on live. Right, so I hope everyone can see the slides, can hear me well, can see my face as well. I see a lot of your faces. So I would like to welcome all of you first to the Seminar in Computer Architecture course. This is our first lecture, and I'm Mohammed Alsar. I will be one of the lecturers for this course. As a prerequisite, I think you have to take the digital design. So I hope everyone already got that course. And for today, we will start with the course logistics. Then we will jump into introduction and basics of computer architecture, why we are studying computer architecture, and what this seminar could enable you to understand, and the things that might benefit you in terms of research and personal growth as well, how to present and further more. So yeah, the role of this course. We will cover fundamental and cutting-edge research papers in computer architecture. And this is one aspect. We will cover other research fields that also get benefit from the computer architecture. So you build architectures and new algorithms to accelerate other applications, for example. So multiple components that are aimed at improving the students' first technical skills in computer architecture, critical thinking and analysis, technical presentation of concepts and papers in both spoken and written forms, because we are going to ask you to write some reports toward the end of the course. And you will get yourself familiar with key research directions. So probably will assign papers that are very recent from our research group and other research groups. So you'll be up to date with whatever we are doing in our research group, for example. And feel free to stop me anytime and ask questions if something is not clear. All right, so the key goal of this course is to learn how to rigorously analyze, present, discuss papers and ideas in computer architecture. As I mentioned, we will assign papers to you so that you can read it first and then analyze it critically, then present it and discuss it with your colleague in the classroom. So steps to achieve the key goal. We have steps for the presenter and steps for the participants. So as a student in this course, you will be for one day as a presenter and for the other days as a participant, where your colleague will present other papers. As a presenter, you need to read the paper that we assign to you, and then you need to absorb, read more papers basically to understand the other related works and how the paper assigned to you compared to the other papers. Then you need to critically analyze it, think about it, synthesize the paper you have. And then you need to prepare a clear and rigorous talk with the help of mentors. So we'll assign a few mentors for each paper. And some of these mentors are basically the author of the paper themselves. So you'll get real benefits from the author of the paper, who wrote the paper, who knows the details, the weaknesses, and so on. After you do this analysis, you will present whatever you have as outcome of your analysis to your colleague. So you will put yourself in the shoes of the author, and you will present the paper in a conference setup. So you will be prepared to present your own.
Jan? Okay, Mohammed, join again. Good.
Mohammed, you are muted.
Oh, sorry. Yeah, I hope the live streaming is still working from your side, John, or anyone can confirm.
Yeah, it's working.
Okay. Yeah. Okay, so let's continue from where I stopped. We have the steps for presenters. So after you read, absorb the paper, you discuss it with the mentors, you prepare a clear and rigorous talk, you will present the paper to your colleague during the classroom. Let me enable the camera. Sorry about that. Okay, I hope now it's fine. All right, so I'm sharing my screen. Okay, yeah, I think we are back now. Yeah, this is the problem of using Zoom and online teaching. All right, so after you analyze the paper and you discuss it with your mentors, so you need to present it and answer some questions. So we have discussion during your presentation and after the presentation, and you need to do some analysis and the synthesis in a meeting, after the meeting, and at the course end. And as a participant, you have some steps. So basically, in each presentation, during the student presentation and our own presentation, you need to discuss the ideas presented in the paper, ask questions that are not clear to you, or you could propose some ideas to improve the paper, or you could also question the idea presented in the paper. You need to do the analysis and the synthesis as the presenter did during the synthesis report or online discussion, in-class discussion, and so on. All right, so the topics of the paper that we are going to assign to you. So we try our best to get a diverse list of papers, starting from hardware security, architecture acceleration mechanism for applications such as medical application and bioinformatics, memory systems, and basically many more. So you can go over the list. And to recap, some goals of this course is first to teach you. So we basically want to teach you how to present any paper, not necessarily related to computer architecture course, but to enable you and empower you to think critically first, how to analyze a paper, how to question an idea, and think broadly. So some ideas that are presented in computer architecture can also be applicable to some other research field. You could, the things accelerated machine learning application, you could use that idea to accelerate something else from something that never been studied before. We will enable you to learn how to understand, analyze, and present paper and research ideas. And as I mentioned, you'll get yourself familiar with key first steps in research, which is doing literature review or analyze existing papers so that you have a solid background about what has been done before, such that when you propose an idea, it's already novel or something that not been done before. You'll get also familiar with key research directions, especially when we talk about our own papers. So most of them are already recent. We will also assign fundamental research papers. So it's not necessarily to be recent. It could be really fundamental, 30 years old, and so on. So this is the cycle of the research or scientific research. First, you need to read papers, read many more, other than the paper assigned to you. And after you read it, you start to question everything in the paper, brainstorm with your colleague, with your professor, and so on. And after that, you will be able to develop new out-of-the-box ideas by seeing many proposed work. Then you might have something new to propose based on what you have read. And you need to collaborate basically with mentors, with colleagues, with other research groups, and work hard with them on brainstorming, improving the idea, and so on. After collaborating, do the work itself, do the evaluation, see the benefits, write a paper, you need to publish that paper. And the publication here, the main goal behind it is to teach the other or educate the others about what you have done. And then the cycle continues. You start reading and solving another problem and so on. All right, so the course info and logistics. So this course is given by Professor Onur Mutlu, who is a professor at ETH since September 2015. He was a professor at Carnegie Mellon University for about 7 years, and he got his PhD from UT Austin. He worked at several companies where he established the computer architecture research group and some of them. And the best way to reach him is to use his email address, Gmail, which is given here. And as a Safari Research Group, our research and teaching is really in different topics, starting from computer architecture, computer systems, hardware security, and bioinformatics. And for this course, we have 2 lecturers, me, myself, Mohammed Alser, and my colleague, Juan. So about myself, I'm interested in bioinformatics, any hardware acceleration for a medical application, genome analysis, computational genomics, and so on. The best way to interact with me is to use the Twitter, Mia Elser. And we have real large number of teaching assistants or mentors. Some of them have PhD, some of them doing PhD at ETH, some of them doing masters and so on. So it really will be nice to know them and their research direction by using this link over here. All right, so what we require from you as a student in this course, first, attendance. Attendance is really important in this course, not only to present paper, but also to attend other presentations. And each student needs to present only single paper. So it's a bit easy task. You spend the entire semester attending other presentation, getting some ideas on how to improve your slides, and then you present in one day. Non-presenters for other presentation need to participate during the meeting and after the meeting as well. Before the meeting, they could ask questions on Moodle and so on. Non-presenters also need to take an online short quiz after each session. So we'll have 5 multiple choice questions for each paper presented. Per day, we may have 2 presentations, then you will have 10 MCQ questions. And you have 4 hours to submit the answers right after the presentation or the lecture. Everyone needs to comment on papers in the online review systems through Moodle. And you need, at the end of the course, to write a synthesis report. And that's all what we require from your side. The course website is already up and available. You can see all the course material posted on the link and other information, other material about the previous semesters and so on. The Moodle is also up. You can check it right now. You can see the announcement, due date, quizzes, paper discussion, assignment submissions, and so on. So we already mentioned the email that we have the homework number 0. We won't have other homeworks. This is the only and this is the first and the only one. And the due is September 30. Just information about yourself. Very simple questions. You need to answer them while you're taking the course, and that's it. But it's very important to submit this homework. Without submitting the homework, it means that you're not interested in the course, so we are not going to assign a paper to you. Basically, you will fail the course. The paper review preferences, we are going to send a list of papers, and you need to show your preferences for a few of them. Not only one, but I think around 8 papers. You need to choose them and then rank them from the most favored one all the way to you don't want such papers. And we will do our best to assign the most favored one to you. It depends on the availability and how many students pick that paper. That's why we ask to rank more than 1 paper, which basically 8 papers. Okay, how to deliver a good talk. So first thing, you need to prepare a slide about the title of the paper you are presenting, the author list, and the venue where this paper was presented. And then you start with the executive summary. What's the problem that the paper is trying to solve? What are the key ideas of the paper, the key insights, and the key mechanisms? What is the implementation and the key results? That is in one slide. And then you start with analyzing the paper. Probably you could start with background before the strength, but after the background, the method that was presented in the paper, you jump into the critiques, the strength of that paper, and the weaknesses. And then you go through the thoughts and ideas that could improve upon this work. And you end up with the takeaways and the discussion starter and question. So basically, your contribution started from the strength, finding the strength, the weaknesses, the ideas, the takeaways, and the discussion starters, and the question to the audience. So these will be your contribution during the presentation. Of course, you need to present the paper before you start with the strength. You'll get more ideas from the mentors as well as from the next few slides about how you prepare these things. Of course, the review should be short and concise. So you have 20 minutes about the review itself. So this is in more details. You need to prepare the first part, which is the problem, the goal, the key ideas, the novelty that the paper presents, the mechanism, the implementation. You need to go in details. If you are presenting, for example, something about bioinformatics, you may want to provide background on that, and then the major results and the conclusion of the paper. Until now, you are just presenting the paper. And then the second part, you will start analyzing the paper or the related work that build upon the paper you are presenting. So in 20 minutes to 25 minutes, you are presenting the paper, and then start with 10 to 20, 25 minutes analyzing the paper. So this is more advice on the paper review. So when doing the paper review and analysis, be very critical. So we don't like, for example, finding the strength that the paper is very nice. Yeah, we know it's nice. Or the paper is well written. That is not something we can consider as a contribution from your side. So you have to really be very critical, questioning the method, the idea itself, how it compares with other research papers, and so on. Always think about better ways of solving the problem or related problems. So what if they use that method to solve the same problem, for example? Why not? Whether it's feasible, costly, more energy efficient, and so on. You could rely on other research papers or articles from companies that discussing the same technique or architecture. So you need to question the problem, read background, and this is what I'm trying to emphasize. You need really to read more papers than the paper assigned to you, especially more recent ones. And you could also look into fundamental papers from the past. And this is really how things progress in science and engineering or anywhere, and really how you can make big leaps by critical analysis. So you cannot propose something novel without knowing what are the weaknesses of the previous work, for example. We will provide a lot of examples, not a few, but really a lot of examples from students in the previous semesters, as well as a presentation from our own research group. If you have any question, you could also stop me, just enable your microphone and you can just speak up. Okay, so I would like also to emphasize that please try to avoid rat hole discussions. What do I mean by rat holes is when you are trying to question the workload. You could also say the author of this paper did not evaluate such workload, but they evaluate another 15 other workloads. None of the research paper can be comprehensive in evaluating all existing workload. This is not the goal of doing research. Doing research, you're proposing an idea, as a proof of concept, you do an evaluation, and you could evaluate it for a few workloads that are important or where you can show the benefits of your proposed idea. You could also evaluate other workload that show the weaknesses of your work. But it's impossible to evaluate all kinds of workloads. That's why you should avoid such discussion. The same thing applies to metrics, performance metrics. You definitely, the paper need to discuss or evaluate important performance metrics, but cannot be comprehensive and evaluate all of them. The configuration, the details, and so on. We always would like to emphasize around the idea, the implementation, and a bit of the evaluation. If the evaluation was great, what was lacking, or if they are trying to hide something in the evaluation, for example, if it is not power efficient, if they are not evaluating the power at all, that is a point to be discussed. We recommend everyone to go through this book. It's a bit old book, around 30 years old, but it has very nice analysis about research stories. And one part about it in this page, where you can see the author shared some of his experience with publication. When he sent the paper to a conference or journal to be published over there, he got some comments, or let's say silly comments, from the reviewers. So he lists some of these comments in this list, and he suggests everyone to avoid such comments when you are reviewing a paper yourself. And one thing that makes everyone working in research angry is when a reviewer asks you why to change the existing architecture. It's working fine. Why we should try processing in memory, for example. The existing GPU or FPGA or CPUs are working fine. And with multi-threading, it can provide speed up. Why to jump into different computing paradigm, for example? So that is something really you should avoid yourself as a student or as a presenter. These are more advices on how to deliver a clear and successful talks. You can follow this link, and you can see some advices like every sentence really matter. Whatever you put in your slide as a content, there should be a reason. Don't put something on the slide and then just skip it, or you don't know how to explain it, or what was the reason behind adding that content to the slide. And the audience prefers not to think. So when you say, for example, in a figure, as I present in this figure, they provide 20x of speed up, you need to highlight that 20x. You need to put a circle where the plot shows really 20x. So don't just give something mystery or cryptic. You really need to be clear, and when you deliver the idea, for example, you need to have clear examples about it. Use animation, use figures, cartoon, images, and so on. Don't give any surprise. Don't show a slide without introducing that slide. Go step by step gradually until you deliver the idea of the paper and move on. All right, so does anyone know who painted this painting? Do we have anyone from Spain? Okay, it was done by an artist called Salvador Dali in 1924. Yeah, I see Adi answering that. Yes, that's good. So if you check the painting of Salvador Dali in the past, they were like, let's say nice, but normal, right? There are a lot of people, talented people can paint something similar to this. But after 12 years, this is also done by the same artist. You can see how fascinating this is done like just 12 years. And you can see the importance of knowing the concept to paint such that you may done fascinating job. And this is what we are trying to do in this course. So we're trying to give you the basic principles, how you present, how you analyze a paper, and give you a lot of examples from all the students. And then you will be able to break these and do something really fascinating, something different than before, and make a successful presentation during conference or during your career and so on. Okay, this is a very important part of this presentation, which is an example from previous semester on how to present successfully. So we had a student in the past, in the previous semester, called Sophie. She joined our research group after taking this course. She really did very well during the course, and she presented this paper. You can access this as an example on how you should deliver your presentation. Unfortunately, we cropped the discussions section from the video because we discussed something confidential about research ideas. But also we provide another examples where it includes end-to-end, the entire lecture, 62 minutes, including the discussion. So that is second example that you could look into on how to prepare a very good example of presentation. We also, Professor Onur, myself, presented a lot of examples during this course and the previous semester. So you can check the list using these links. You can access our playlist on YouTube. You can see a lot of examples along with the slides in PDF and PPTX. You can also check the course webpage. If you go to the this section, you will see the past course materials. You can access all of them and see again the YouTube list, examples of the slides from the lecturer as well as the students. All right, so how to participate? First, you need to come prepared to the lecture. Even if it is not your own presentation, you should read the paper that's going to be presented. You need to read it, critically evaluate the paper, and think about new ideas. What are the things that you are going to ask about? Or what are the things that you still have doubt about it, or questions, or it's not clear to you when you read the paper? And then ask it to the presenter. You have to participate in the discussion during the presentation and after the presentation, and also during the online discussion through Moodle. You have to be critical, as we mentioned several times. You need to brainstorm with your colleague, with the presenter, with the author of the paper. So be open to new ideas, for example. This is the same applies to the presenter. You have to pay attention and discuss and contribute. The discussion is a major part of this course. Without discussing, you may not be able to develop new ideas or have a critical way of thinking about how to find the weaknesses of the paper. So this is a good practice until your presentation day. You need to participate in the discussion, in all presentation, until it's really the time for you to present. You need to participate during the class, in the online session, and also offline with your colleague, if you like so, or with the presenter. The guided talk preparation. First, you need to check your presentation date. So after you enter your preferences for the paper that you'd like to present, we will assign the paper and we'll assign the date when you are going to present it throughout the course. So once you know that date, you have to start early preparing for your own presentation. And then you need to study it. So carefully, critically, and creatively. So you can try examples by hand. If the method presenting the paper show an example, you need to present that example, or you could find a better way to explain the method, the discussion, the idea behind the work. And you of course, you need to animate the way you present the slides, the figures, and all this stuff. You need to create draft presentation after you prepare the material that you are going to present. And once you prepare draft presentation, you will meet with the mentors, not only once, but twice at least. You could ask for a third time to meet with the mentors. The mentors will give you a lot of comments, feedback on what is clear, what is not clear. You need to fix all these issues, and that should happen before your presentation date. So you should well in advance contact with your mentors that we are also going to assign to you. So you already know who will be your mentors, but you need to contact them really in advance, at least a month or month and a half before your presentation date, and then ask them, I'm going to prepare this, and I expect the draft to be ready on this. Can we meet on this date? And then after the first meeting, you're going to arrange for the second meeting, the third, fourth, until you are ready. Meetings are really mandatory. Without meeting at least twice with the mentors, you are not going to present. That will make you failing the course. So this is very important. All right, how about the grades? So 60% is just for the presentation. So it's very important to deliver a clear and successful presentation. And what I was trying to deliver is how to make that successful presentation. So please follow the examples that we provided, follow all this guidance, and also follow the mentor's comments. So if they provide you comments, you have to address them. You could also argue if they are not applicable, but for sure you need to address them, either by accepting or rejecting these comments from the mentors. But be sure or be assured that these mentors are really the author of the paper most of the time. So if they say something, then it should be true. And 30% of the grade is going to the final synthesis report, which you are going to submit after a month from the last lecture. So normally we give you 30 to 40 days to submit this synthesis report, and we assign it on the last lecture day. So you have 30% on that, and then 10% on the quizzes after each lecture. As I mentioned, there are 10 MCQ questions. You need to answer them, and that will give you the 10%. There's a bonus 10% in total for the participation during class and online. So that's it for the grades and the feedback. We will try to briefly discuss the strengths, the weaknesses of your talk in class. So Professor Onur Mutlu or any of us will give you the feedback on what went wrong during your presentation after your discussion with your colleague. So once the discussion is done, we will give you comments right away, and also you can get more comments from the mentors. As I mentioned, you need really to arrange the meeting with the TA to get the feedback. All right, so the expected schedule, and that is the last for the logistics. So we will meet once in a week with 2 presentations per session. The next meeting should be next week. Next week, probably it will be an example on how to review papers. So you're not going to start presenting, but student presentation will start on 7th October. That will be the first 2 presentations from students. Currently, there are 27 students registered in this course. So we expect to have 27 presentations. Each presentation is about 15 minutes, including question and discussion. As I mentioned, the paper assignment will be done online. Study the list of papers, check your email and be responsive. Make sure the Moodle is already, when you got the notification through Moodle, you got also the same notification in your email. So you need to activate your email through Moodle. Don't forget to submit the homework. You have about a few days to submit it. As I mentioned, this is very important. Otherwise, we will not assign a paper to you to be presented, and thus you will fail the course. So it's very important to solve that homework. And the preferences for paper review will be, we will send more details on that through Moodle, hopefully this week or on Monday, the latest. And that's all for the logistics. I hope I cover most of the aspects or the question you have in mind. Feel free to send question on Moodle as well, or you can ask right now. If we don't have questions, we can jump directly to Juan, who will present about the basics of computer architecture. John Fertina, if you have any questions from your side in the classroom. Okay, great. There is no questions from the classroom. Yeah, I would like to thank everyone attending in the classroom as well. All right, Juan, I'm done. You can start sharing your screen.
Very good, thank you, Mohammed.
Thanks.
I'm sharing now. I hope you all can see my screen, can see my face, and can also hear me. Okay, thank you everyone for joining this course and for joining this online lecture. My name is Juan Gomez Luna, and I'm the 3rd instructor in this course. In this part of the lecture today, what I'm going to do is giving you some more introduction about this seminar, and I'm also going to give you a few preliminary ideas about some of the different research topics that we are going to cover in this course. Yeah. Okay. So, well, you already know Professor Mutlu. He is a professor at ETH in the IT department. As Mohammed already explained in the previous presentation, the best way to contact him is his Gmail address, and he does, and his group does research and teaching in many different things in computer architecture, computing systems, hardware security, and bioinformatics, and then many aspects of these, let's say, main trends. So from all these trends, we have, let's say, kind of main research directions. Just give me 1 second. For some reason, I cannot see my screen properly. Okay, anyway, I see this banner from Zoom all the time, and it's hiding the title of my slide. But anyway, it's fine. Okay, so okay, so as I was saying, we have, let's say, our group has a current research mission. Essentially, this is building fundamentally better architectures, and this does not only, I mean, it encompasses the whole amount of components that we have in a computing system, from the processors and accelerators or graphic processing units to the main memory system and the storage system as well. There are 4 key current trends in our research, or current lines in our research: fundamentally secure, reliable, safe architectures, fundamentally energy efficient architectures with a big focus on memory-centric and data-centric architectures. We are going to talk about some of these today: fundamentally low latency and predictable architectures, and architectures for AI, machine learning, genomics, medicine, and health. Before I continue, by the way, I would like to say that we have quite a few slides in this presentation. I don't know if this will last longer than 6 p.m. If that's the case, and you guys have a lot of duties to pay attention to after 6 p.m., please don't hesitate to go and deal with them. You can watch this lecture online later, because this is being recorded. One more thing is that we are also going to have, and we actually have already in the website, one optional lecture. It's already available to you in the website, and I think that we are also going to release a recording soon. Okay, so I was talking about the 4 research lines, key research lines. And if you're familiar with, I mean, if you have taken, probably most of you have taken the Digital Design on Computer Architecture course by Professor Mutlu, I'm pretty sure that you remember this figure, the transformation hierarchy. So when we talk about computer, or when people talk about computer architecture, they usually focus on these 2 layers of the whole stack. Remember that the whole stack grows from the problem and the algorithm up to the bottommost components, which are the electrons and the devices, right? And computer architecture is usually restricted to this area here, the software and hardware interface and the microarchitecture. But our view here is much wider. It's an expanded view that goes from the algorithm to the device. And the aim of doing that is because this way we can understand the workloads and the algorithms much better, and also the devices themselves, and communicate and connect everything in a much better way and seamless way, and make computer architectures more efficient. And this is actually one key action that we have, is to achieve the highest energy and performance. And not only that, also other goals that we want to achieve in computer architecture, and will be a focus on this course as well. Other goals, like, for example, cost, like, for example, the amount of silicon area that you need, and so on. So if you want to achieve all of these, you must take expanded view of computer architecture, right? So it's something that spans from the topmost layers of this computing stack to the bottommost ones. And by doing this co-design across the hierarchy from algorithms to the device, we can achieve these goals much better and specialize much more. We will see several examples over this presentation about specialized computer architectures that are tailored, that are specifically designed for certain type of workloads. But we are also going to talk about more general purpose architectures like CPUs and GPUs, which need to somehow exploit correctly the trade-offs, because they should be more or less good for all types of workloads. And we will see as well that it may be possible to either reconfigure these architectures or use them when they are really good for certain workloads. And this way, we are going to make also these general purpose architectures more efficient. Okay, so as I was saying, current research mission is build fundamentally better computer architectures. You can see here some of the major topics that we work on in our group: data-centric architectures, low latency and predictable architectures, fundamentally secure, reliable and safe architectures, and architectures for ML, AI, graph processing, genomics, and other types of applications, and data-driven, data-aware architectures that can take advantage of the data, the data that they handle, and analyze this data in order to make intelligent decisions. As we will also see some examples of that in this presentation, and for sure later in the course. Okay, so this is a picture of some of the people in the Safari research group. It's a very large group. As you can see, we are currently, I would say, more than 40 people. This is our motto, think big and high. As you can see in the picture, Mohammed and me, it's here. And this one is Professor Mutlu. He unfortunately could not attend today, but for sure he will be with you next Thursday. If you want to learn more about our research group, I'm going to talk more in this presentation, but I would definitely recommend you as well this presentation by Professor Mutlu, introducing the group and introducing our research. And you can also know more about the group by reading the newsletter that we release from time to time. The most recent one is from January this year. In order to disseminate our research and also the research of other people, specialists in different areas of computer architecture, we have started this summer a series of seminars that we call Safari Live Seminar. And we have already delivered, as you can see in the slide, 7 talks, very interesting, all of them. You can access the recordings of these talks from this link that you have here from our website, and also invite you to the next of these lectures, these seminars, which will take place on Monday. Christina will give her talk about efficient synchronization support for near data processing architectures. I can tell you that this is very good work and very interesting talk. And actually, this may also be one of the the readings that we will suggest in this seminar. Okay, so you can find all these recording, all these past seminars in Professor Mutlu's and in our YouTube channel. Here you can find these live seminars, you can find special courses. For sure, you can find all lectures from the undergraduate and graduate courses, also from this seminar, and many more useful resources. So for example, something that you can access from there is the playlist of lectures from the Digital Design and Computer Architecture course. As you know, and as Mohammed already mentioned, this is a prerequisite for this course. If you haven't taken or Digital Design and Computer Architecture course, I'm pretty sure that you have taken similar courses with some of the same contents. But in that case, and also if you have already taken the course, I would definitely recommend you to take a look at these lectures and also the website of the course. You are going to see it in the next slide, because this can be a very nice refresher in digital design and computer architecture before we go deeper into this course. And also some useful resources you will find as well in the computer architecture graduate course that also starts these days, the fall 2021 edition, but all the recordings from previous year are already available in YouTube. This is the website. Here you have the link to the website and the link to the playlist of digital design and computer architecture. And this is the same for the computer architecture graduate course. And many more resources that you have at handy are all the tools that we develop in our group. They are outcomes from our research projects. We open source everything. They are available to everyone in our GitHub. Here you have you can see a screenshot of this GitHub here in this slide, and the next one you have some direct links to some of the repositories in the GitHub, and you can find many more here. Actually, you can see already in this slide a very long list, and I can tell you that most of these are from 2020, the oldest. So imagine the amount of resources that are available in this GitHub. And here you have the different links. So if you want to go to Professor Mutlu's publications, you have these two. So his website, his Google Scholar, and then you have the link to the YouTube channel and the link to the GitHub repository. Okay, and why do we make all these resources available to you and to everyone else? Because we believe that teaching is extremely important. It's important to educate people, and it's important to drive research. If you learn the fundamental topics, if you learn the basics, you will be able to apply that on your research. But also research drives teaching in the sense that research gets incorporated into teaching at some point. Whenever we work, I'm saying we or research group or other research group develop something important, something useful that creates an impact in computer architecture, in all research, this ends up being incorporated to the curriculum such that it can also be taught to students in the future. So this is kind of a virtuous cycle. So it's like a continuous feedback from teaching to research and from research to teaching. So some principles from our group and some principles that you have to take into account when taking this course. We focus on insight and we encourage new ideas. You will see, and probably we will talk about this also at some point in the course, you will see that there are always people who are skeptical, people who are reluctant to start adopting new technologies. In the end, if you focus on new ideas and you develop good new ideas, they will end up creating an impact, not only in the academic world, but also in the industrial world and the commercial products. So that's something that you can see and you will see in some of the papers that you are going to read and discuss over the course of the semester. You will see what's the impact that they made on the real world and on the commercial products. And also focus on learning and scholarship. So that's important as well. We are here to learn, and we are here also to help others to learn as well. So in the end, one key goal is to create an environment that values free exploration, openness, collaboration, hard work, and creativity. Because this way you will achieve high quality work, and the quality of your work is the way you have to define your impact. And in the end, what you want to do is to make a good impact on the world. So if you want to watch some inspiring and motivating talks from Professor Mutlu, I would definitely recommend you this list. We are going to talk again about some of these, like for example, in-memory computing or the story of RowHammer. Later in this presentation, you have this list available here for your convenience. More interesting talks from Professor Mutlu about computing research and education, if you want to understand well his views of these reflections on DRAM, or how to build an impactful research group, do's and don'ts of creating a research group. Or why computer architecture is so important today. This is also something that we are going to talk about today. And by the way, even if you are interested in doing research in the future, so you may end up applying to graduate schools, I would definitely recommend you this talk that he delivered at the mentoring workshop at ISCA this year, the ISCA conference this year. And you can find here a screenshot of this talk and the link to the YouTube video. Okay, so how to take this course, how to approach this course. I mean, I think that Mohammed already explain the different things that you need to do to pass this course and that you will have to do over the course of the semester. But also one thing that I would like you to know is what's the opinion of some of our past students, because for sure their words are going to inspire you as well. So these words in this slide and the later slides are from the opinions that we have got from our students when surveying them in the final synthesis report that you will have to submit as well. They consider the course like a formative experience. They think, or some of them think, that reading and analyzing papers will help them or will help you a lot into the future. And why is that? Because by reading a research paper and analyzing it, you're going to develop your critical thinking, and this is going to benefit your understanding of whatever you learn in the future, and will also allow you to make better decisions. So that's why it's important. This is not going to be for free. For sure, you will have to work hard, and that's what we expect from you. I mean, compared to other courses, it's not really that much, right? Because here, essentially, what you have to do is studying a paper, analyzing it, preparing a presentation, and delivering your presentation, and then discuss the paper with the rest of the group. But we expect that you work hard when preparing this. So in the end, this is high investment, but it also will be high return. For sure, you are going to learn a lot from the paper that you analyze and study, and from the discussions and attending the presentations from your classmates. And also, you're not going to be alone. As Mohammed already explained as well, you're going to receive guidance from researchers who work in the field, as also some of the students applied in the past. And hopefully by the end of the course, you will say the same as many of them. I would definitely recommend this course, and probably many of you are here today as well because you have received the recommendation from a colleague. And maybe even hopefully some of you will end up expressing your love for computer architecture. So take this as a very good learning experience. Think about the long-term trade-off, what you are going to learn and how this is going to be useful in the future. And it's going to allow you to develop your critical thinking and your decision-making abilities. Okay, so after having introduced our group and also having introduced this seminar, you know already why you are in the seminar, because you want to learn more about computer architecture. But now a good question to ask ourselves is, why study computer architecture, right? So let's start defining what's computer architecture. We can define it as the science and art of designing computing platforms, hardware, interface, system software, and programming models in order to achieve a set of design goals. For example, obtain the highest performance, or the longest battery life, which is extremely important these days with the amount of mobile systems that we are using, or achieve the best average performance across many workloads, right? This connects to something that I said before. We see more and more specialization these days in computer architectures because they are very important workloads that require to achieve the maximum performance and energy efficiency. And we are designing accelerators and we are designing specific architectures for these specific workloads. But we still need to keep using general purpose processors like CPUs or GPUs, where maybe they may not be perfectly fitted or suitable for all types of workloads, but for sure, we will try to achieve the best possible performance and energy efficiency for all these types of workloads in these systems. And we will discuss as well different ways of achieving those goals in the general purpose processors. So many more goals that you can think about. And as you will see as well, designing a supercomputer is different from designing a smartphone, because different platforms have different requirements, because they also typically work on different applications as well. But one important thing to take into account here is that many fundamental principles are the same. And actually, if you go deeper into the systems and understand them well, what are their different components, you will see that they essentially have the same components. So for example, these two platforms are for two different goals. A desktop computer is not the same as a cell phone, but in the end, they have a general purpose processor, like a CPU. They need to have a graphics processing unit. They have some accelerators. They have a memory and a storage system. So they share a lot of common components, even though the dimensioning, let's say, and the configurations of these components is different because the platforms themselves are intended to be efficient on different goals and on different applications. This is another example device, right? And one drone. We talked recently about edge computing when it comes to placing compute capabilities in these edge devices like drones, right? And here we also have a trade-off: is where do we have to place our computation? If we put more computation here in the drone, we are going to probably save a lot of energy and a lot of time from moving the data that the drone and the sensors in the drone capture from moving all this information to somewhere else, to the cloud, right? But on the other side, if we place more computation here, we will have more requirements for battery. We will have, and in the end, we will have to also have the right setup to placing here the compute elements, right? So there are always trade-offs, and you are going to be able to analyze these trade-offs as well when studying your paper. More platforms, self-driving cars. This is a very nice example, and here you can see the internals of one of these self-driving cars and the big, I would say, computer, almost a small data center that the self-driving car needs to process all the information that is coming from different sensors in different parts of the car, like vision sensors, for example, that capture the image. And here, probably some artificial intelligence or machine learning algorithms are going to analyze that data and make decisions afterwards. Or another example, this one, data centers, right? In particular, this one is the Tihange 2 supercomputer, which was the fastest supercomputer of the world until, I don't know, 2 years ago or so. Here, again, components are very similar, but challenges are also different. For example, in these kind of systems, one big challenge is the cooling system, right? You have such a large amount of processors generating heat that you need to somehow dissipate all that heat. And I was mentioning before, specialized platforms, right? We more and more design architectures for specialized workloads. And this is a very good example presented at ISCA 2017, the tensor processing unit designed and developed by Google. If you guys have taken the digital design computer architecture course, I'm pretty sure you remember it because Professor Mutlu explains systolic arrays in one of the lectures, and this is essentially a systolic array, right? We are going to feed from one side, we will feed the input images. From the other side, we will feed the neural network weights, the weights of the different layers, and then a matrix multiplication is going to happen. And in the end, that's like the key operation in many of these machine learning workloads. By the way, machine learning is not only neural networks or deep neural networks, which are very successfully used these days. There are many more machine learning techniques that can be useful for many different topics. For example, reinforcement learning that, as you will probably see in some of the examples in this course, can be used, for example, to handle computer architecture more efficiently. Here you have another good example of an ML accelerator related to the previous one, right? But of course, for the specific needs that the application has, this is developed by Tesla, so it's a chip for self-driving cars. So here we have two redundant chips because this is a safety critical application, right? So different platform because the goal is different than the one that we may have in the previous accelerator, even though the type of workloads are going to be similar, but the conditions where each of them are going to operate. One of them will be probably in a data center. The other one is going to be in a self-driving car. Different needs require somehow different designs as well. Okay, so going back to what's computer architecture is the science and art of designing, selecting, and interconnecting hardware components and designing the hardware-software interface to create a computing system that meets functional, performance, energy consumption, cost, or other specific goals. So that's what we want you to learn in this course, in the digital design and computer architecture course, and in the graduate computer architecture course, which maybe some of you already taking or will take in the future. And in order to achieve these goals, recall, we don't want this narrow view of computer architecture. We prefer expanded view of computer architecture, because this way we are going to be able to enable better systems, computers that are going to be faster, cheaper, smaller, more reliable. We are going to be able to enable new applications, and that's something that has already happened in the last 10 years, I would say. You have already seen, or you are experiencing the rise of machine learning and artificial intelligence, and how booming all these applications are starting to be using completely different fields, right? From medical applications to genomics to, as I mentioned before, for example, controlling computing systems and make them more efficient and so on. And if you think about that, why this didn't happen 10 years ago or 15 years ago? So if we look back, we will see that about 12, 13 years ago, more general purpose, because the first, let's say, general purpose architecture was the NVIDIA CUDA architecture, and these allowed programmers to use the GPU not only for graphics, as it had been done for 20, 30 years, but also for other general purpose computations, right? And the fact that all this immense amount of computing power was available to researchers allowed some of them to try deep neural networks on them. And by using GPUs to train deep neural networks, they were able to train them much faster and make them really usable. That combined to the fact that nowadays we are also in the big data era, and there are many more data accessible to everyone for training all these machine learning algorithms. So we have seen this revolution that has just happened, let's say, and this has been enabled by computer architectures. So in the end, our goal is to enable better solutions to better problems, and that's why to problems, and that's why computer architectures. So that's why computer architecture evolves the way it's evolving, and that's why it's important for us and for you to understand it well and understand why computers work the way they do. So today is a very exciting time to study computer architecture, not only because in the academic part, in the academic side, there is a lot of activities, innovations, and new ideas that are being explored, but also because industry is taking a paradigm shift. So I mentioned before, that you will always find people who will reject ideas, who will be skeptical, who will be reluctant to start using new devices or new technologies. But fortunately, the industry is changing as well, and we are going to see soon some good examples of this, because this way we can solve much better many difficult problems that motivate all this research and all this innovation. And you can see some of these, some of these important problems here. We will actually talk today about some of them. For example, the memory bottleneck, the fact that data usually resides very far from the processors, right? So we typically, you recall the von Neumann model, we typically have the CPU here, we have memory here, and in between we have a narrow memory channel, right? So every time that we need to access data, it takes the CPU a lot of execution cycles and a lot of energy to get the data from memory. So a way of dealing with that memory bottleneck or data movement bottleneck is to deploy a paradigm shift, for example, that actually was proposed decades ago, but it's today when it's actually becoming a reality. And this paradigm shift is processing in memory or reliability problems. We see that as technology scales, we have more and more reliability problems in the devices. A very good example of this is the RowHammer phenomenon that I'm pretty sure that all of you know, and we are also going to review later in this presentation. But there are no clear and definitive answers to these problems. So we need to keep doing research and finding good ways of dealing with the different problems. So these problems affect all parts of the computing stacks, and that's why we have to change the way we design systems, because as well the problems are evolving over time. So for example, these days there are many new demands from the top. For example, problems change, algorithms change, and new algorithmic techniques appear or start being important. I mentioned machine learning and AI, but also we have many new issues at the bottom, right? For example, I just mentioned the RowHammer problem is a good example of the issues that come with technology scaling. And also on the top, even the demands from the society and the personalities of the users are changing. So that's why the computer architecture also needs to continue evolving. And actually, if you look at computer architectures today, you will see that the computing landscape is very different from what it was 1 or 2 decades ago, right? It's different from in the upper part, the software and the humanity trends, and it's also different at the bottom layers, right? The technology and so on. So that's what we have to do, re-examining all the components of the system, make them more efficient, adapt them to the new challenges of the new times and to the new problems and applications that appear or start becoming important. Again, our axiom: to achieve the highest energy efficiency and performance, we must take the expanded view of computer architecture. And this way, we will be able to co-design across the hierarchy from the algorithm to the device and specialize much more in order to achieve the design goals. And that's something that was also referred by the physicist Richard Feynman many years ago, that his famous talk, "There's plenty room at the bottom," where he talked about the possibility of directly manipulating individual atoms to make systems more powerful, right? So I'm pretty sure that at the very beginning, there were many people who were skeptical about this word, but at some point, nanotechnology started to become a reality. And actually, this was a very good, important reference for them. Feynman had in mind the possibility of building denser computer circuitry, and he was also thinking about the possibility of swallowing the doctor. These days, we don't think that it will be so difficult to have these kind of swallowable surgical robots that can be very good at many health and medicine applications. And definitely this important famous lecture created an impact on many researchers from later years. And we have also one good example in this paper. There is plenty of room at the top. And there is also something interesting here that you can read in the abstract, is that opportunities for growth in computing performance will still be available, especially at the top of the computing technology stack: software, algorithms, and hardware architecture. So this is the transformation hierarchy that we talk about, and this is why we need this expanded view of computer architecture, because there is plenty of room at the top, plenty of room at the bottom, but much more so when you communicate well and optimize across all the layers of the computing stack from the top to the bottom. So, so again, or expanded view of computer architecture. And actually, I'm going to start giving you some examples, some research examples, how this is possible to be enabled, how we can enable all these seamless communication across layers. One of the ideas that have been proposed by students of our group is the design of cross-layer abstractions that allow the system to expose certain characteristics of the hardware to the upper layers of the stack. When we talk about the upper layers of the stack, we talk about the programmers, we talk about the compilers, how they can make use in a much more direct way, how they can make use of the characteristics of the hardware. So imagine that you have, like, for example, different types of prefetcher in your system, right? And you know your workload, you know how you want these prefetchers to work. So by using these cross-layer abstractions, it will be possible for you to configure these prefetchers to be more efficient for the specific workloads that you want to run in your system. And this is not only for prefetching, this can also be for cache management, page placement, memory compression, making decisions, for example, based on approximating values and approximating results, and many more things. And not only for CPUs, also for GPUs, like, for example, this locality descriptor, which is for GPUs. So usually when you are programming a GPU, it's not the same the way that you need to access data depending on what are the characteristics of the workload, right? For example, if you are just, let's say, going over a whole array of data because you want to, for example, perform a vector addition, you just need to access in a string, right? One element after the other. So that will benefit from certain ways of accessing memory, where we take advantage of the large DRAM row buffers, or for example, we can make use of next line prefetchers that are going to bring the next cache line that is going to be accessed next, right? But if you, for example, are operating on a data structure that is two-dimensional, like, for example, an image or a matrix, you probably prefer to access in a two-dimensional way, right? By dividing the whole data structure into two-dimensional tiles that are going to be assigned to the working threads, and accessing these two-dimensional tile is different from accessing in streaming, right? Especially because, as you know, in memory, data is stored in a linear manner. And if you need to access one tile, we are not going to be accessing consecutive locations when we move from one row to the next row of the tile. So providing the programmer with the ability of defining what's optimal for the memory access that the workload needs to carry out, that's definitely going to be very beneficial in terms of performance and energy efficiency. And you can see in these slides more examples, for example, for heterogeneous memories with different levels of reliability. You can also read this approach to deep neural inference using approximate DRAM, Eden, which was presented in Micro 2019, or Smash is also a very nice example of hardware-software co-design to accelerate sparse matrix computations on CPUs. And also another very good example is this virtual block interface. It connects very well to this idea of the cross-layer abstractions and this idea of making the hardware more available to the upper layers of the stack. Here, the key idea is replacing the conventional virtual memory framework with something that is much more flexible and better supported by the hardware that allow you to, let's say, make the memory allocations and memory management in a much more tailored manner to the specific needs of the applications or the hardware itself. So many interesting things are happening today in computer architecture, as I was saying, and we are going to keep seeing more. Some of them relate to performance and energy efficiency. We said before that these are two of the key goals that lead us to try to design and build better computing systems. One very good example is this Intel Optane persistent memory that was released in 2019, 2 years ago. This is essentially a replacement of the conventional DRAM that you can already go and buy and install it in your system, but it's different in the sense that it's not DRAM. This is a non-volatile memory that is likely built with phase change memory. And good thing of using this memory, of course, it also has some drawbacks, but some good advantages as well is that you can integrate more, you can have larger chips with this 3D X-point technology. And also it's non-volatile, which means that you don't need to refresh as you have to do in DRAM. So these advantages may be very beneficial for certain applications, right? And this is something that, as I said, was launched 2 years ago, but it's something that has been explored for many more years. So for example, this seminal paper from Professor Mutlu that was presented in 2019 is already about how to architect PCM phase change memory to make it a scalable replacement and alternative to DRAM. So notice how the research that was done in 2019 became a reality 10 years later. And here you can see another version of the same work. This is an IEEE micro journal, so it's probably more accessible to everyone. Another very good example of how computer architecture works on creating systems that provide higher performance and energy efficiency, especially if we focus on certain workloads. This is a Cerebrus wafer scale engine from 2019. It's the largest ML accelerator chip. If you look at this, it's not a chip, actually. It looks like more or less like a tablet, right? So as you can actually compare the total size of the Cerebrus in the same scale at the largest GPU, and you can see how much larger it is. And why it is so large? Because of two key reasons, I would say. First of all, because for machine learning workloads, you typically want or need a lot of memory space, and you also need a lot of computation and also parallel computation. Why is that? Because deep neural networks and other machine learning algorithms require a lot of access to data, accessing, for example, the weights of the filters, accessing the input images when they are training, and also they need to repeat. They need to perform certain operations that are very frequent, but have the good thing that they can be executed in parallel, right? So here the idea in this wafer scale engine is to have a lot of small tiles containing small single units attached to SRAM memory that is going to store the inputs and is going to store the weights, right? And because the computation in these algorithms is relatively, or is quite regular as well, it's feasible to map all this computation onto all these units, computing units, and orchestrate the communication across them as it's needed. And here you can see the next version, the wafer scale engine 2 from 2021, essentially is twice the number of cores and actually the size of the total SRAM, and also still much larger chip than the largest GPU that this year in 2021 is the A100 from NVIDIA. And also other interesting architectures for performance and energy efficiency. I introduced before processing in memory as a way of alleviating what we call the data movement or the memory bottleneck, right? So this is a trend that was actually, these are ideas that were actually proposed decades ago. The oldest paper that I'm aware of was published in 1969. And essentially the idea was the same. I have this memory bus that it's connecting the CPU and the memory, they are very far from each other. Every time that I need to go to memory, I'm going to spend a lot of cycles, I'm going to spend a lot of energy. So why don't we put some processing elements, some processing capability inside the memory, right? So this is an old idea, but for different reasons, technology challenges, no one built, or at least no one commercialized such an architecture. So 2 years ago, the French company UpMem already designed and fabricated and started to commercialize these PIM-enabled DIMMs. As you can see, they look as conventional DRAM DIMMs with chips, but the special thing in these chips is that they include some small processors called DRAM processing units, or DPUs. And here you can see another picture of one of these systems. It's actually one of the ones we are working on. In total, this one has 2,560 DPUs. These are small processors that are inside the DRAM chips. You can see in this system, find in this system 2 multi-core CPUs. There are some DIMMs of conventional DRAM that keep working as the main memory of the system. And then we have some DIMMs of PIM-enabled memory. In particular, in this system, we have 20 DIMMs of this PIM-enabled memory. If you want to learn more, you can already watch this talk that I delivered a couple of months ago, and actually was the first of our Safari Live seminars that I mentioned and introduced in the beginning of this lecture. And by the way, UpMem, it's a relatively unknown company probably for many of you, but I'm pretty sure that you all know Samsung, right? So what UpMem did was being the first one to commercialize a processing in memory architecture, a processing in memory system. And it's clear that they are going, and they are on the right path, because a big company, a large manufacturer like Samsung is already doing the same. Samsung has recently released their architecture called FIMDRAM, which essentially is, again, processing in memory for AI, for artificial intelligence. You can read about this FIMDRAM architecture from Samsung in their ISSCC paper, and also in their more recent ISCA paper that was presented last June. The FIMDRAM architecture essentially consists of one cube of HBM2 memory, and in each of these layers, there are layers that are only for memory, like these ones on top, and there are also other layers that are compute capable, let's say. So actually, in some of the in these layers, you can find these programmable compute units. It looks like a relatively conventional SIMD unit where we have a pipeline decoder, and we have then an array with different lanes that can perform certain operations. In particular, they are specialized for multiplication and addition, because as for sure you know, these are key operations in many machine learning algorithms, and especially in deep neural networks. So they are, let's say, application specific, but still programmable, right? And this is kind of the layout of the thing. This is one of the layers. So here you can identify different banks. This is bank 0, this is bank 1, and every 2 banks there is one of these PCU blocks that contain this SIMD pipeline that executes multiply and accumulate operations for machine learning workloads. So it's different from the UpMem architecture in the sense that it's more application specific, while the UpMem architecture has a more complete instruction set for many other workloads. Samsung has even more recently released the DDR5 version of this processing in memory architecture. And here you also see the title of one of the recent papers where they compare a baseline system with one of these PIM-enabled systems for recommendation systems. And you can see, well, the pictures from the setup in this slide. But this processing in memory, as I said, this is not something that started in 2019 with Upman. This is much older, right? 50 years older, actually. And it's not only older because it started 50 years ago, but also because a lot of research has been done in recent years as well, until it really became a reality and became commercially available. And for sure, there will be many more things to do from academia and from industry. Our group has been working for a while on this trend, on this main trend, or this main paradigm shift of processing in memory. And actually, we typically distinguish among our works two main approaches. The first one is what we call processing near memory. The second one is what we call processing using memory. We're going to very briefly explain what's the difference. In processing near memory, you typically have your memory array, and what you're going to do is placing some compute units closer near this memory array, right? So that's why we call it processing near memory. Processing using memory is when we use the memory itself to perform the computations. And you're going to see a very good example soon. And actually, for sure, some of the papers that we will discuss in this course will be about processing using memory. But let me first talk about processing near memory, or some of the papers that our work has published and have created an impact in the community for sure, and also maybe papers that we will discuss in this course. So, for example, this first one is a scalable processing in memory accelerator for parallel graph processing. It's called Tesseract, and this is essentially like a large accelerator composed by many or by several HMC 3D stack memory cubes, each of them containing some small processor in the logic layer of this 3D stack memory, and they can communicate with each other in order to access different parts of the graph and perform very efficiently. You will have access here to the presentation and also to the paper. You can see the amazing speedups and energy savings that you can achieve compared to other types of devices like CPUs. Another very interesting example, more or less from the same time as well, are these beam-enabled instructions. Observe that here the approach is completely different. Why is that? Because in the first case, in the case of Tesseract, we are proposing a whole accelerator that can execute very efficiently a particular workload. We were talking about type of workloads. We were talking about graph processing as well, about graph processing. Here in beam-enabled instructions, the key idea is to identify instructions that are very frequently used and are important for the execution of certain workloads, and place small units that are specialized on these operations closer to memory. Examples that you can find in this paper also span graph processing, because, for example, accumulate operations to update certain values when we are doing page rank, for example, we need to update a value, add another value that has been generated before. That's one potential usage. In image processing, for example, you can create a histogram, and these are all like very small and simple operations that can actually occupy very small area inside the memory, but can execute very efficiently these applications and achieve interesting performance and energy benefits. Another, okay. Okay, another example work paper from our group in ASCLOS 2018, these Google workloads for consumer devices, also very interesting paper, probably also one of the ones that we will propose for discussion in this course. It's analyzing Google consumer workloads, like for example, Google Chrome or the VP9 video encoder and decoder, analyze what are the data movement bottlenecks, and propose processing in memory solutions for these Google consumer workloads. Or Synchron, the efficient synchronization support for the near data processing that I mentioned before, because this will be the talk that Christina will deliver on Monday. So think about the architectures that we are discussing, and we are talking about the Tesseract architecture, for example, that is composed by multiple cubes, and these cubes have small processors that need to communicate among each other. We also need to want to do that in an efficient way, right? And there are also not only proposals for CPU systems, also for GPUs, like for example, Tom paper published in ISCA 2016, or these scheduling techniques for GPU architectures, and many more, as you can find in this presentation for specific workloads, like for example, pointer chasing operations. This is a proposal that performs the pointer chasing calculations inside memory, or ways of accelerating cache misses, or fetching data that is going to be used in advance. This is a continuous run ahead, which is inspired by the run ahead engine proposed by Professor Muldo in his PhD thesis. This is adapts this run ahead idea onto the memory controller in order to bring data more efficiently to the cache hierarchy of the CPU system, for example. And then we have other examples of accelerators, like these stencil accelerator, near memory stencil accelerator for weather prediction modeling, or this one for accelerating genomics workloads, or this one for time series analysis, or here we have another one, FPGA-based near memory acceleration for modern data-intensive applications. In this particular paper, we talk about the weather prediction that I just mentioned before, but also genomic workloads like sneaky snake algorithm developed by Mohammed in his PhD thesis. Maybe we'll talk about it soon as well. But if we want to make good use of these processing in memory architectures, we also need to know and understand the workloads very well, right? Because this is not just like saying, oh, I have this feature here, I'm going to start using. I mean, maybe you go and pay the money for one of these Samsung DRAM memories, and then you place it in your system, and then you realize that your workloads don't have multiplication and addition. So in that case, probably you cannot use them, right? So that's a joke, but the truth is that we really need to understand the workloads very well to identify those parts of the workload that can benefit more from these new paradigms, like for example, processing in memory. And I would definitely recommend you to take a look at this DAMOVE methodology and benchmark suite. We have evaluated here more than 100 important workloads, and we have obtained very interesting conclusions and takeaways related to their data movement bottlenecks. As you will see, there are we identified like 6 main classes of workloads depending on what are their data movement bottlenecks. And also, you can learn more by watching this seminar given by Geraldo. That was also one of our Safari Live seminars. It's totally available in YouTube. Okay, so I'm done with the first part of the first approach, processing near memory. The second one is processing using memory. So the key idea in the processing using memory is that we are going to exploit the analog operation, the analog capability of memories, of the memory cells, in order to perform some sort of operations. The very first example, and actually that's what corresponds to the title of this slide, comes from 2013, is the, actually I have it here, is the RowClone paper. This first paper in this direction proposes a way of doing both data copying and initialization in a very efficient way inside the DRAM subarray. The key idea here is that we have 2 rows, we have 1 source row, we have 1 destination row, and the key idea of the RowClone bulk data copy and initialization is that we activate 1 row, we load it into the row buffer, and after that we activate the destination row, and we write the whole row buffer into this, the contents of the row buffer into this destination row. And that can enable very fast bulk copy and initialization, as I said, with amazing speedups and energy savings. And this is also for sure one of the papers that you will become familiar with over the course of this semester. Same as the Ambit paper, also proposed by Vivek. In Ambit, the key idea is to activate several rows at the same time in such a way that those DRAM memory cells, DRAM cells that share the same bit line are going to share their charge onto the bit line at the same time. And this produces a majority operation. In the end, if you have 2 zeros and 1 1, you will end up having a 1 0 in the sense amplifier. If you have 2 1s and 1 0, you will end up having 1 1 in the sense amplifier. And with this majority operation, you can create other bitwise operations like AND or OR. And as you know, if you have AND, OR, and NOT, and the paper also proposes a way of doing NOT, if you have the 3 of them, you're functionally complete and you can create whatever operations you want. And that's actually what we did in this SIMDRAM paper presented in ASPLOS 2021. It's a for sure very interesting framework to see the way of exploiting end-to-end this ability of performing computation using memory. Okay, so this is RowClone, and RowClone, by the way, connects to another big challenge of processing using memory, is the fact that, okay, you can maybe do copy inside the same subarray, you can maybe perform some with bitwise operations with AND-bit inside the same subarray, but after doing some computation, for example, performing the element-wise addition of 2 arrays that are stored in different rows of the same subarray, we may need to use the output data in a different place, right? So one potential way is to read the whole row that is stored in DRAM and move it to the CPU and then back to another place. If we need to move inside the same subarray, it's fine, we can use RowClone, but if we need to move across subarrays, that's not that easy, right? We need to figure out a way. And this was proposed in 2016, the LISA paper that enables the inter-subarray data movement. And there are later proposals as well as Figaro or as this non-paper that propose more fine-grained ways of moving data internally inside DRAM. Related to processing using memory as well, we have other proposals that relate to security, the ability to implement security primitives inside DRAM, like for example, the DRAM latency path and the D-range that allow you to, by operating DRAM at low latency, you can create paths, physically unclonable functions, and random numbers. If you want to read a good summary of all these works and actually many more, I would definitely recommend you this book chapter, A Modern Primer on Processing in Memory, that we released very recently. And also you have another paper here. This is more like a workload-driven perspective, but also connected to some of the same works that I just mentioned before. Okay, you can learn more from Professor Mutlu, this tutorial on processing in memory, memory-centric computing systems. And here you have this screenshot from the talk and the link to the YouTube channel, and many more lectures about processing in memory. These are coming from the computer architecture course from the last fall 2020 semester. Computation in memory, near data processing, memory controllers, and real processing in DRAM with AppMem, right? Which is relates to the talk that I also mentioned before about the AppMem architecture. And here you have even more emerging memory technologies, etc. Okay, so recall we were talking about one of the key goals, or two of the key goals of computer architecture. More performance, more energy efficiency. We already talked about this one, for example, the Tesla ML accelerator, and also about the TPUs and these these accelerators or specialized processors keep improving, right? So we talked before about the first Google TPU from 2017, but now there is a new version from, no, actually this one is from 2016, this one is from 2017. If I wrongly read the title of the slide, it's because I still have this banner from Zoom, and I unfortunately cannot hide it today. Anyway, yeah, so the second version, much more powerful. As you can see, total teraflops is essentially twice as large, but also much more higher bandwidth because this one is using HBM, high bandwidth memory, instead of DDR3 as the previous generation. And we have even a more powerful one in the TPU version 3 that actually I think was released this year. And here you have the title of the original paper and some explanation about how the systolic array works, and a few more details here. I'm pretty sure that most of you are already familiar with this architecture. And as I said, if you want to remind how this works, I would definitely recommend you to go back to the lecture on systolic arrays that Professor Mutlu gives in the DDCA course. Okay, and these are not the only efforts to create accelerators, specialized architectures for machine learning and AI. You can see here a list of other companies that are also working on or have already created their own accelerators. And these are major vendors, as you can see, but also many more companies, startups, and much smaller companies as well are working on these AI chips, benchmarks, compilers, and many other tools that are needed to really make the systems efficient for the specific workloads that we talk about, machine learning and AI workloads. But many more things are still happening. Many more interesting things are still happening in computer architecture. Other important goals, security and reliability. And this takes us to talk about the RowHammer phenomenon that you for sure are already familiar with. And essentially in the RowHammer, as you may remember, one can predictably induce bit flips in commodity DRAM chips. And the original paper showed that more than 80% of the tested DRAM chips are vulnerable. And this RowHammer phenomenon is the first example of a simple hardware failure mechanism that can become or create a widespread system security vulnerability. The media have paid a lot of attention at the RowHammer phenomenon, as you can see here in this article. Let me very quickly remind you how RowHammer operates. Essentially, the thing is that every time that you open and close a row, there is a perturbation in the bit line, and this perturbation, when it's repeated on the same row, affects the neighboring rows and makes that some bit flips appear in the neighboring rows. So if we are hammering one row, we will see some bit flips in the adjacent rows, which are these victim rows. And this is a phenomenon you may remember even this slide from the original paper in 2014. More than 80% of the DRAM chips are affected by that time by the RowHammer phenomenon. And the problem with it is that it can provide ways of exploiting this vulnerability and becoming an actual attack, an actual security threat. And that's what a few months later, after the publication of the ISCA 2014 paper, the Project Zero team at Google even improved the original assembly code that was used to test the RowHammer, and by exploiting this RowHammer bug, they were able to gain kernel privileges. And this is not the only work that has done that, as we can see in later slides. And one famous hacker wrote this cool sentence about the RowHammer phenomenon. It's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibration opened the door you were after, right? So I think it's a very good analogy. And here you can see more examples of attacks performed by using RowHammer. This is using JavaScript. This is on Android mobile systems. This is another way of doing it in Android phones by taking advantage or making use of the GPU. Keep in mind that all these mobile phones and essentially many of these mobile devices also integrate a a small GPU next to the CPU that can access the same memory space, and the GPU, because it's like much more parallel machine, has the ability to even create more memory requests, and these memory requests are going to perform the attack, and so it can be even more efficient by being done by the GPU. Another example is RowHammer to a remote location using the RDMA interface. This is another example also using RDMA. This is a very interesting example as well about how to leak data from chips by using RowClone, or other examples about how to attack deep neural networks. This one published in the Unique Security 2019, and this is 1 year after. So imagine all the amount of literature that has come after this original RowHammer paper. And actually, like 2 years ago, Professor Mutlu wrote this retrospective paper with Jeremy, who was one of his PhD students, and also was one of the original, the authors of the original paper. Super interesting read that I could recommend you. And our group keeps, not only our group, many other groups in the world, but especially our group keeps doing research in RowHammer. These are some works published last year in 2020. This one presented by Jeremy at ISCA, like revisiting RowHammer. It's like, okay, let's, a few years after, like 6 years after, let's take a look at how the RowHammer problem goes in all these new DRAM chips. And you will see that actually there are very interesting conclusions. One of the important ones is that chips are even more vulnerable to RowHammer, and this is something that makes sense because the technology, you know, the scales, the devices, the circuits are much more smaller, so they are even less reliable, and that's why with as low number of hammers like this 4800, for example, you can already flip bits in adjacent rows. More works, for example, there's Trespass that exploits the target row refresh, which was by its time announced as one of the solutions, or one golden solution, let's say, for the RowHammer problem. But actually, we have shown that there are ways of bypassing this protection and continue performing RowHammer attacks. So for sure, more solutions and better solutions are needed for this problem. And this one for sure is a good one. Blockhammer that Girai presented this year in February at HPCA is a way of preventing the RowHammer attacks by giving the memory controller the ability to detect those DRAM rows that are very frequently accessed. And so they are hammer rows, and blacklist them, meaning putting them on hold and have accesses to other rows in order to avoid the RowHammer attack. This for sure will also be a very interesting reading and also an interesting paper for this course. If you want to learn more, you can for sure read all these papers, but I would definitely recommend you this talk by Professor Mutlu, The Story of RowHammer, and even more lectures about RowHammer from the Computer Architecture course, and this beautiful picture. And RowHammer is not the only hardware-related type of attack, right? For sure, you have also heard about Meltdown and Inspector. This is more an architectural attack in the sense that, you know, RowHammer is a failure of the device itself. It's based on the physics. You start hammering one row, and the perturbation, opening and closing the row, provokes the errors in the adjacent rows. Here, even though the design might be good, but the architecture, unfortunately, allows some exploits. Like the key idea in both Meltdown and Inspector is that someone can steal secret data from the system, even though the program and the data are perfectly correct and the hardware behaves according to the specification. There is no actual hardware failure as we have seen in RowHammer, and there are no software vulnerabilities or bugs. But because of the fact that computers have been over the years designed for higher performance without taking into account security, without guaranteeing the security, very efficient techniques, like especially speculative execution, have been proposed. But the problem with this speculative execution is that it leaves traces that can be of secret data, and an attacker can have access to these secret data that somehow leaves the trace in the cache, right? And there are ways for the attacker to infer the secret data that has resides in the cache. And even a malicious program can force another program to speculatively execute code that leaves traces. This is probably one of the candidate papers, at least, and we have discussed both Meltdown and Inspector in past editions of the course. And actually, if you want to read more about this, I would recommend you this channel, and also about this channel, this article from the Project Zero team, and where they also talk about other vulnerabilities as well. Last news about RowHammer is that 2 of our papers about RowHammer got accepted at Micro 2021 and will be presented at this conference in the next weeks, actually, in very few weeks. I think it's in October. Yeah, so this is the first one, this paper led by Lois and Giray, and this is another one led by Hassan, also again about the protection mechanisms and a new methodology to figure out what are these protection mechanisms. So many things are, interesting things are happening today in computer architecture. Now I'm going to stop sharing because Mohammed will take over from here. I don't know if there are any questions from you. I don't see any questions in the chat. If you have any questions, you can ask now, or maybe you can reach out to me, Mohammed, and Professor Mutlu later after the presentation. Thank you very much for your attention.
Okay, that was great, Juan. Thank you so much. If no questions, probably I can start directly. John, do we have questions on your side? Okay, seems no. Do we have a question, by the way, on YouTube? Any question from the folks watching online? Okay, yeah. So I will have about 40 slides, but hopefully I will finish it in about 10 minutes or so. So basically, as you can see from the slides that Juan presented, that more demanding workloads and more to come as well, that we may think they are still doing okay, but we still need really to build a customized and specialized hardware architecture, especially for important problems that are sometimes life-threatening, such as medical applications. And basically, you need to be dreamer. So dream and they will come. All these architecture, even if they are doing well these days, but at some point they will reach the boundaries, and you need to really re-examine every part of the architecture. And one example of this is, yeah. Sorry, my camera was off. And one important example of this is genome analysis. So unfortunately, with all the advancement in this field since about more than 40 or 50 years working on this field from many other research groups, so until now, we don't have any machine that can get the genetic sample and give you a full sequence of your genome. What we have is basically what we call whole genome analysis, or a whole genome sequencing pipeline that needs some processing at the wet lab, where you process the genetic sample and you give it to a machine called sequencing machine. And this sequencing machine gives the pieces of your DNA. It's not a range, it's not one sequence, but large amount of pieces of your DNA or genetic material. And the problem becomes now computational because these pieces are just string, ACGT, and such. So the computational problem or the computer science problem is how to map or to link these pieces together. That's why we call it read mapping step. And then after you build these pieces together, you build the full sequence of DNA, then you do what we call genomic variant calling, where we can recognize variation or genetic variation that may cause some disease, or what makes basically an individual different from another individual using phenotypes or such. So these sequencing machines still provide a small randomized fragments of the original DNA. And in this paper, we study, for example, one of the machine coming from the company called Nanopore Sequencing or Oxford Nanopore Company. And the device, you can see it's almost the same size as the hand and called MinION. It can provide a large throughput of sequencing data, which are the reads, the pieces of your DNA. And this sequencing machine is really sophisticated just to do sequencing step. However, we still lack of compute power. So we still need to send these data to huge clusters or large or capable computer to perform the analysis, either read mapping or the downstream analysis. So we really need customized devices to follow up with this sequencing machine. And as you can see in this one important example, the data here is the main performance and energy bottleneck. And just to give you an example about, or an idea about how these sequencing machines perform, they can process 48 human whole genome at 30x coverage in about 2 days. That is to say, in 1 hour, they can process the entire human genome. And 30x coverage means I'm reading the same location, your genome, 30 times, so that I'm increasing the confidence that my reading was correct. And as you know, this sequencing machine sometimes makes error, and these errors need to be addressed or fixed using some computational steps. However, when we look at the CPU or current CPUs, we need, for single human genome, 32 CPU hours to process such amount. So you can see the wide gap between the performance of sequencing and the performance of the analysis. And the answer is simple. Why we have such gap? Because we are using for sequencing something customized, really sophisticated, specialized just to do sequencing. But for the analysis, we are using general purpose computers. So we have wide range of sequencing machines. They can do with high parallelism, many samples on the same time. We also have very small devices such as this attached to iPhone, where you can do the analysis on the phone, for example, or where we have these devices with GPU cards to do the analysis. When we look at the history, we can see there are increase in the throughput of this sequencing machine over time. But when we look at the Moore's law, we see it's constant. And the progress, when we compare sequencing with the Moore's law, we can see that the gap is really widening more and more as the throughput of this sequencing machine and as the cost of the sequencing itself getting reduced significantly. And that will lead to sequencing many more organisms. Because now these days you're not paying $1,000 per sample, but rather $100 or less per sample to do the sequencing or the analysis. And there are even kits available in the pharmacies, in the supermarkets, where you can do the analysis yourself. You take the swab and you send this swab to the sender again, where they do the analysis and give you full report of your genetic material. So by that, it could be the analysis just for out of curiosity, just you'd like to know what's going on with your DNA. And that will make really the analysis the bottleneck, because sequencing now is way cheaper than before and way capable than before. And when we look at the genome analysis, trying to figure out what is the bottleneck, how to make it faster, you can see the read mapping and then variant calling. And then the variant calling will lead to identify some SNPs or genetic variation that cause some genotype or phenotypes. And this is a huge amount of data, still a bottleneck. And someone could ask why we really need the analysis to be fast. I can send my sample to the clinic and they could take 2 days to give me the results. I'm fine with that. Why I need faster analysis? So there are really life-threatening applications. For example, think about a critically sick child in a hospital, and you don't know what medicine to give him because simply you don't know from the symptoms. You cannot decide what disease he has or she has. And for that, you need really to check his genetic material. And based on the genetic material, you have some cases in the past that you know they were getting better because they got this medication, but not the other medication. And for that, you really need to decide quickly because some of these children have few days, could be 2 days, 1 day to getting better or just simply die because of wrong medication. And there are a lot of papers showing the benefits of doing whole genome sequencing quickly, and that provide or avoid morbidity and reduce the hospital stay length and the cost significantly. And for that, UK started to have whole genome sequencing for all seriously ill children starting from 2019. So you can think about the need for a really scalable analysis where you are ready to do the analysis or the sequencing for all admitted children at a day. So we are not talking about the execution time for singular analysis, but rather how scalable you can go, how many DNA you can process in a single day, for example. Another application is where you are interested to know what kind of microbiome you have in a city or in a crowd. Think about very crowded city. If you have very dangerous microbiome, that can cause death to a large number of people. And for that, the government normally do regular check on the microbiome in train station, hospitals, in ICU units, in space shuttles, and so on. So there is a very huge study was done in New York City in 2015, and they did it at city scale. And this year, we have another study that was done at the population scale. So they include 60 cities. So think about when you want to include even all train station in a single country or the entire continent and so on. So that is something, a huge workload to be processed by today compute paradigm or compute capabilities. Third example, when we have Ebola or COVID-19, you can think about the same thing. When we have outbreak, disease outbreak, and you want to do the analysis or you want to really monitor the situation over there, so you would like to swap everything and see what kind of medication may affect these cases or what kind of monitoring or controlling may be more effective than other controls and so on. So for that, you need a very large scale analysis. Not only that, but you could do these in remote areas where you don't have access to the internet, so you cannot use a cloud, you cannot use large clusters, and you need something portable because you might do this using the ocean or desert or really very far areas where you don't have infrastructure to do the analysis. So looking for further customized hardware for the analysis is now is a must, I would say. And this is a huge amount of sequencing machines shipped from UK to China to support the COVID-19. This was, I think, last year. So think about in one package how many sequencing machine we have, but if we want to ship compute power like clusters or PCs, what will be the space for that? So you have the sequencing machine, very small, generating a large amount of data, but the compute capability is still huge. or at least it's still limited and not specialized to the problem we have. There are a huge amount of large number of examples that we can mention here, where we really need very fast genome analysis. It could be understanding genetic variation or predicting the presence and relative abundance of microbes in a sample, or it could be a rapid surveillance of disease outbreaks, or even developing personalized medicine, as I mentioned in the previous examples. So just to sum up, we need really intelligent algorithms and intelligent architecture that handle data well. So building architecture alone is not enough, because you really need algorithms that understand the underlying architectures, and you really need architectures that support the algorithms. That's why when we have UpMem or any of these new compute paradigm, you really need to build sophisticated algorithms that understand the architecture such that we can leverage the full compute power of these devices. This is our recent paper where we did analysis to all type of acceleration that was done to accelerate read mapping, which is a very important step in genome analysis, and it's one of the main bottleneck in the entire pipeline. Another bottleneck we could look at is the base calling itself. It's still a time expensive, computationally expensive step, and need to be really accelerated. This is a summary of the things that we did in our research group, Sapphire Research Group. So we look at the full stack of today computers. So we have the sequencing machine here, sending the data to the storage unit, and then to the main memory, then to the different level of caches, and then the CPU. So what we did at the CPU side, or between to replace the CPU with customized hardware accelerators, is we have a couple of work trying to do pre-alignment filtering. And I think in the next lecture, or maybe the one after, we're going to explain in details about this work as an example of how to review papers. So what is pre-alignment filtering is try to detect quickly where are one of these pieces generated by the sequencer that differ significantly from what we call a reference genome. So one way to do read mapping is to try to attach these small pieces we got as a read together. And to attach them together, we need to solve it as a puzzle. So you have a reference picture where you look which piece can perfectly attach to one place in that reference picture. And that's what we call reference genome. And then try to attach each of these pieces to that reference genome, and then we stick them together so that we know the exact place. However, we try to compare every read or every piece coming from the sequencer with large number of locations in the reference genome. And we see if they really similar to each other or they have a lot of differences. If there are a lot of differences, probably this nonsense and doesn't make any meaningful inference, and that's why we need to get rid of that piece and just ignore it and move on with the next piece, try to find the best location in the reference genome. Once we are done, we already built your target genome. And we also did processing in memory or near memory with multiple works. And finally, we did a near memory sequence alignment, which is the very last step that can tell you exactly where are the differences and the similarity. So in pre-alignment filtering, we don't care about the location of these similarity or the differences. We just want to know quickly how many differences are there. So if they are exceeding a threshold, then probably this is not something interesting, and then we just remove it or get rid of it. But if they are less than a threshold, then the question is, where are these differences? And if they are at an interesting location that we know this location might cause a disease, then we really need to know the type of that difference, whether it's substitution, insertion, deletion, and many more. So this is the paper that I was talking about, pre-alignment filtering, called Gatekeeper. Feel free to download the source code. It's available for the FPGA and for the CPU, so you can change it and improve it. The same for Grim filter, which is processing in memory, based the pre-alignment filter. We have Shurji, which is FPGA based. We have Sneaky Snake, which was built for CPUs, GPUs, and FPGAs. We have also Genasm, which is specialized hardware for processing near memory, and the source code is also available. These are more papers about an overview of the entire topic and evaluation of existing work, how to cluster them, which one providing full accuracy, which one try to sacrifice the accuracy to gain more speed up, and so on. In this work, we try to improve upon Sneaky Snake. So using near memory, we achieve more energy efficient pre-alignment filtering, as well as very fast processing. This is our recent paper, just published in Genome Biology, which is one of the top journals in genomics. And we try to study the history of this problem for the last 30 years or so. So what we are trying to solve using our research projects is when we move from this paradigm to something similar to this, or even smaller and more advanced, are we ready to move to fully portable genome analysis pipeline where we don't need computers at all, or we don't need large hardware or large clusters, large cloud, or and such devices. So this will enable doing the analysis anywhere, even in space. So I think in the news last month, SpaceX was going to carry microbiome studies in space to see the effect of these space shuttles on the microbiome or human gut, for example, microbiome analysis. So for that, you really need portable devices. You don't want to carry a large infrastructure to space, and you don't want to access cluster over there to overwhelm the communication between the space shuttle and the Earth, for example. You could also enable such analysis on Moon and so on. So we're still not ready for that yet. This is the latest device from ONT, Oxford Nanopore. We can see the sequencing is taking time as much as the analysis, and this is the best we can do. This is about RNA analysis. Think about when we talk about metagenomics, for example, where we have a huge amount of reference genomes, because we are not targeting single individual, but rather we want to know all type of microbiome we have in a sample. So we cannot compare to a single reference genome, but we need a large database of all existing reference genomes, or some of them. And for that, the analysis is taking way longer than just doing the analysis for single individual. You can see the Oxford Nanopore devices are enabling more application and more sequencing data for different type of species. And we still are not ready to do the analysis for all these different type of pipelines efficiently. To get more details on this topic, I recommend everyone to watch my 3-hour lecture on this topic in detail. So you can access the link, it's already available online. You can access the slides. You can also, I highly recommend everyone to watch this lecture from Professor Onur Mutlu. The video, the slides, all are available on our website. You can access using these links. These are more papers, talks, and survey papers on the topic. You can access them. You can exactly use the same insight, the same mindset we have for genomics for many other applications that is still generating a huge amount of data that overwhelm the compute system and make the performance and the energy bottlenecks. These are many more. And in this paper, for example, you can think about this huge amount of data when you want to move it from the edge devices where you generate the data to the storage devices, all the way to the main memory and then to the CPU. And that huge amount of energy spent just to move these data without doing the processing. So there's about 62% of the total system energy spent only on data movement. So think about doing the processing inside the memory or near the storage or even near where the data is produced. So just to give you an example about this data movement issue, you can see that the memory access consumes about 100 to 1000x the energy of a complex addition. So just to do a complex addition, that is way cheaper than just accessing the main memory. There are many interesting things that are happening today in computer architecture, especially with enabling all these kind of applications. And some of them are really important to address. We really need a customized hardware to do the analysis, and general purpose computer are not doing well for these applications. And for that, many novel concepts investigated and re-examined today, especially the computing paradigms. So the processing in memory is not something new. It's already been there for, I think, about 30 to 40 years. But the enabling such paradigm to be effective, it was happening recently because of the tsunami of data we have these days. So trying to rethink the full stack for each application, because some application might benefit from processing in memory, but some of other application might benefit more from processing near storage, or vice versa. So we cannot have one architecture that fit all these applications, but rather we need to re-examine at every stage and every kind of application. We can see a lot of new accelerators proposed for artificial intelligence, machine learning, graph analytics, and genome analysis. New memories and storage systems are also enabled by this application or by the need for accelerating these applications. So as we always say, so be dreamer and all will come. So the applications always push the boundaries, and the compute platforms will become increasingly strained. Remember about the data movement bottleneck? So think about where to place these processing. We have different stages, different architecture to replace the CPU or the main memory or the storage and so on. So that is getting the architecture from very simple paradigm to very complex paradigm. So the computer architecture today, we have the computing landscape is very different from what we have 10 to 20 years ago. So these days we have more capabilities, more architecture that support processing in memory, as Juan explained, and many of these examples from real companies, from real startup, and the applications and technology both demand novel architectures. So every component and its interface, as well as the entire system design, are already being re-examined for different applications. You can revolutionize the way computers are built if you understand both the hardware and the software and change each accordingly. As I said, proposing a new hardware architecture is not enough. If you don't change the algorithm and make it hardware friendly, you may not get the same benefits as if you propose a new algorithm and new hardware customized for the algorithm in hand. You can invent new paradigms for sure for computation, communication, and storage if that provide benefits to the application. We recommend reading these two books for further details. And as key takeaways, so it is an exciting time to be understanding and designing computing architectures. As you will see in many of the papers, hopefully will be presented in this semester, you will see various examples where these applications really get huge benefits just by tweaking the architecture or proposing something new. There are still many challenging and exciting problems in platform design that no one has tackled or thought about before. For example, in genome analysis, when we started in about 2014, Professor Honor also started working on that in about 2007 or so. So there was very limited number of research groups working on this. But these days, I see the number of research groups working on genome analysis or accelerating genome analysis really getting more and more, getting larger. And that is good for this area, but it's still not as many research groups as those working for machine learning, for example, or artificial intelligence and so on. That can have a huge impact on the world future, as I already explained in many of the examples. Some of them really will make a difference in our life if we could build these customized hardware for genome analysis or personalized medicine or metagenomics studies and so on. So driven by huge hunger for data, we are always generating data, and these data sometimes are just wasted because we cannot analyze them on time. There are new applications enabled by this data, and we are still lacking efficient hardware that are built for these applications. Driven by significant difficulties in keeping up with that hunger at the technology layer, there are 5 walls: energy, reliability, complexity, security, and scalability. And when we are talking a very specific application, there might be more walls. For example, when we are talking about genomics, directly the privacy issue will arise, or legal concerns, and so on. So that was all from our side. So sorry for taking more time, but I'm really, these topics very close to my heart, and I like talking about these topics and working on these topics. So normally after this course, we typically hire some of the students to work with us in our research group with Professor Onur Mutlu on some of the research projects that we have at all levels. It could be semester project, it could be just for fun, or it could be master's project, PhD, and so on. So yeah, keep up with the papers we have in our course, and I hope all of you will do well in this course. And if you have a question, we can take them through Moodle or now, if you would like so. I hope all logistics were clear. You know what to do, how to be successful in this course. Okay, don't forget to submit the homework, and we will send you the paper preferences very soon, hopefully this week. And that's it. Thank you so much, and take care of yourself. Hope everyone will stay safe and healthy during this semester and the following semesters. Yeah, take care.
Thank you, Mohammed, and thank you, everyone.
Thanks, Juan.